Topic 8.2, World Energy Sources. So in this section of the text, we're going to outline some of the energy sources of the Earth, for the human beings that is, where we get our energy from, and some of the basic advantages and disadvantages, and we'll sort of classify our energy sources in various different ways. And one of the most obvious ways for us to categorize the energy sources is in terms of their being renewable or non-renewable. Now obviously we would prefer to have renewable energy sources that we can reuse over and over again, but most of our energy sources now are non-renewable. Our non-renewable energy sources include things like coal, oil and gas, nuclear fission, and nuclear fusion. Now many of these sources are what are referred to as fuels, and that is that once they are gone, they're gone. Our renewable energy sources include solar, hydroelectric, wind power, wave power, tidal power, or energy directly from the earth called geothermal power. So how does it actually play out in the world? What percentage of these different types of energy sources do we actually rely on? And as you can see, oil and gas combined account for more than 60% of the world's energy resources. Combined with coal, another fuel, that takes us up to almost 87% of the energy resources coming from those three. Now hydroelectric accounts for 6%, and that is a renewable energy source, but then we go back to nuclear, 6%, which is a non-renewable energy source. And finally we hit all the geothermal, solar, wind, wood, tidal power. These only account for 1%, meaning that right now we only use 7% of our energy resources are renewable, and that's a big problem. Now most of our energy resources come from something called fuel, and fuel is very simply defined as a substance that can release energy by changing its chemical potential or its nuclear potential energy. That is to say, they are somehow either burned or undergo a nuclear reaction in which the atoms or the nuclear particles rearrange themselves into a less energetic form and therefore release some of their energy that we can then go ahead and use. So let's take a closer look at how we get some of the various fuels, and let's start with oil and gas. Oil and gas are related to each other because they are formed by the same process, and much of our gas comes from the oil itself. It turns out oil and gas is actually a product of very tiny organisms called phytoplankton and zooplankton. And at various times of the earth, these organisms have lived in enormous quantities, and when they died, they collected on the bottom of the seafloor, eventually mixed with various types of rock like limestone or with sand, and were compressed at a very deep depth until eventually they were turned into oil and gas. Now ultimately these oil and gases then become trapped under rocks which are called impermeable. Impermeable meaning that water or liquids cannot flow through them. So you can see in this picture that we drill down through very tough, very resistant rocks to where the oil traps actually are, and then the way that we actually get the oil out is that we force water down. We force water down into it, and then of course oil is lighter or less dense and it gets pushed up through the wells. Recently it's been an issue in the news that we want to start offshore drilling. So these are oil deposits that are just off the coast of the US. And it's a bit of a problem because of course some of that oil may escape and become part of an environmental issue, but we find that oil is trapped anywhere where we see the continent. We do see these sort of oil traps. So what do you get from a barrel of oil? Well, you can see the bulk that we get from the oil is gasoline. Of the 40, actually technically 42 gallons in a barrel, we get 19.5 gallons of gasoline. That's a pretty good amount. We also get distillate fuel oil that are used for various other types of services, jet fuel, residual fuel. You'll see we get kerosene up at the top up there. We get oil that we use for asphalt. This is the blacktop roads. We get a lot out of a barrel of oil. It's an extremely useful thing. And of course, obviously, one of the main things that we use it for is our cars. Gasoline. We get 19.5 gallons of gasoline for every 42 gallons of oil. So most of it turns into gas. And of course that creates a bit of a problem because gasoline has to be burned to release the fuel, and that produces what we call greenhouse gases. Now besides fueling our cars, we can also create electrical power by heating up, by burning the oil or gasoline to turn water into steam. The steam turns a turbine, that turns an electric generator, and that sends electricity out to our houses. Now obviously the United States is one of the main consumers of oil. As you can see, we have a variety of sources, Canada, Mexico, South America, Africa, and Saudi Arabia are the bulk of our imports, but we do get a small amount from Europe also. This is something that we would like to eliminate, our dependence on foreign oil. You'll hear them often talk about this in political conversation. So next, let's take a look at coal, which is one of our also very heavily used resources and another form of fuel. And coal formed by a slightly different process. Coal forms in what would generally be referred to as swamps. These are very stagnant, low-lying areas where tremendous amounts of biological material begin to accumulate. And there are periods of times, particularly in the period before the dinosaurs, a period called the Carboniferous, and then a short period at the end of the dinosaurs where swamps persisted worldwide and collected tremendous amounts of plant material, which ultimately was turned into coal. Now, how do we get the coal? Well, unfortunately, there's a bit of a problem. We can't force it to the surface like we were able to do with the oil by pumping water in. So instead, we have to dig for it. Now, it tends to be much less expensive. Rather than dig tunnels and pulling the coal out through these very narrow tunnels, it tends to actually be cheaper to do a process called strip mining, where we literally strip the entire surface of the earth off above the coal mine, and then we can just simply dig it out directly. Now, this causes a bit of a problem environmentally speaking, because of course we've dramatically altered the landscape, and then we leave a tremendously large gaping hole that has to either be filled in with water or filled back in with terrain. Now, once we've stripped away the surface, that makes it very easy for us to go ahead and use heavy equipment to dig out the coal, and then that coal is ultimately deposited into trucks. The trucks take it to trains, and the trains ultimately end up transporting it to the factories that are going to actually use the coal. Once the coal arrives at the factory, it's dumped in big piles and then slowly fed into a furnace, which is of course turning water into steam, and the steam is turning a turbine, which turns a generator and sends out electrical power. Now, one of the big issues with burning coal, of course, is that anything that we burn releases greenhouse gases, particularly carbon dioxide, and of course they do talk about clean coal, but in reality there is no such thing as clean coal. Now, if you look at the United States, you would see that we do have quite an abundance of coal, and actually Europe also has a fairly large abundance of coal. Illinois itself actually is one of the main suppliers of coal, but you can see in the Chicago area, if you look closely at the map, you'll see that there is not very much coal around the Chicago area. Most of our coal comes from the downstate area, and then we also actually do have oil in the downstate areas of Illinois, and this is because most of central and southern Illinois was entirely a large swamp approximately 350 to 400 million years ago. Now, when we think about fuels, we only have a very small number of what we would consider renewable fuel sources, and these are wood and biomass. Now, of course, wood has been used since the beginning of human times, not to produce electricity, but simply to produce thermal energy, to release it in its most efficient form, which is to get back the heat. Now, of course, it does produce greenhouse gases, just like any other substance which is burned, but wood is something that is renewable, and in addition to that, wood also absorbs some of the carbon gases while it's growing. Now, in addition to burning wood, we can also create biofuels from using corn. Corn is one of the big things that's in the news right now, because it turns out that corn produces a tremendous amount of oil. That oil can be used, of course, to cook with, but it can actually be turned into a form of diesel, which can then be put directly into your car. In fact, you don't really need to even modify the car very much. And so that's what's created this caption or this image where somebody is jamming a piece of corn into their car. You literally can run your car off fuel made from corn. Now, the problem with that is that, of course, if you use corn to produce fuel, then that makes the price of corn go up, because corn becomes a much more valuable commodity, and then that therefore causes the price of food to also go up. So there's a little bit of a trade-off. Although we can produce a renewable energy source, unfortunately we cannot use all of the land on Earth for producing biofuels, because we need food. And so that's what caused this cartoon, where we are using food which is desperately needed in parts of the world where they have very little food, to power our cars, which are really tend to be a little overused in the United States. And that brings us to our last fuels, the nuclear fuels. And nuclear fission is one that we've been very successful with, and this simply starts off by concentrating uranium, which is in the form of uranium oxide, mixing it with carbon, and then they send small pellets down into a metallic rod, and the rods are assembled together. These are actual pellets that you can see, the small black pellets. Again, they're mixed with carbon so that they're relatively concentrated, but not too concentrated. and then these are slid into a small metallic rod. That rod is then put together with a bunch of other small rods, and then this produces what we call the uranium rods, which are actually a series of much smaller rods. So these nuclear fuel rods are then stored in tanks of water because they are literally warm to the touch, not because of the fission, but because it's a radioactive substance, and radioactive substances give off decay particles, and those decay particles cause the materials surrounding them to heat up. And essentially the nuclear power works in a similar sense to the way that we use when we burn fuels, and that is that the reactor core becomes very hot, it heats up water. Now if you notice closely, you'll see that the water doesn't actually directly turn the turbine. Instead, that superheated water under very high pressure goes into another tank of water where it transfers. This is called the heat exchanger, and then that water is turned into steam, which eventually turns the turbine and the electric generator. Now, the big issue with nuclear power plants is not about the greenhouse gases that they produce, but instead the spent fuel rods. What do we do with all of these fuel rods once the uranium-235 has mostly been undergone the fission process and is no longer there? And frankly, we really don't know. At this point, though, we have had nuclear power for quite a while, for almost 40 years, I should say, and we have produced a tremendous amount of radioactive waste for which we have not yet transported to its final destination, and this could be a problem in the future. And this brings us to nuclear fusion, and this is the process that powers our sun, of course, and while not technically a renewable resource, only tiny amounts of hydrogen are required to release enormous amounts of energy. Again, the only problem being the sun. It's very easy to contain that 10 million degree temperature plasma, but how do we as human beings contain it? So the concept is that we use magnetic fields to control the charged particles, and we keep them going around and around in circles in what's called a toroid. Toroid is basically a donut-shaped object. Now essentially what happens at that point is that we inject material into those that can feel the heat from those the plasma, the torus-shaped plasma of material, and that of course creates the hot water. The water turns into steam, the steam turns the turbine turns the generator, and ultimately we end up with electrical power. Now we have actually produced these devices. Unfortunately, we have not been able to make them commercially viable because it takes more energy to keep this thing contained than we get out of it. So obviously that's sort of a wash. It's not useful at this time. So that brings us to the end of our discussion of fuels as a source of energy. But before we leave, let's discuss this term called energy density. And energy density is simply the amount of energy per unit mass, and we typically measure that in the number of megajoules per kilogram of that particular fuel. So let's take a look at some of the different fuels. And notice how much energy we get from the fusion or the fission process. Although we haven't mastered fusion, we certainly have mastered fission, and we get 90 million megajoules for 1 kilogram of nuclear material. This is mostly uranium-235. Then we drop down from the millions to only in the tens of megajoules per kilogram. Now remember that fusion doesn't account for any of our power, and fission only accounts for about 6% of the energy of the world. Most of it comes from the petrol, which only has approximately 47 megajoules per kilogram, the biodiesel, the crude, the coal. These are our main sources. But actually you can burn sugar or wood and you get a pretty fair amount of energy from these guys. It's approximately 17 megajoules per kilogram. You can actually burn cow poop and you get 15 megajoules per kilogram, which is actually a pretty fair amount of energy, but it's not considered a very high grade energy. And in fact you can even burn waste. The garbage that you send out to the garbage man can be burned to produce a small amount of energy. So now let's take a look at some of our non-fuel based energy sources, and in fact it turns out almost all of these energy sources are renewable instead of non-renewable. And the first one we'll take a look at is solar. Now it turns out almost all of our energy ultimately comes from the sun. Anyone who's ever used a solar powered calculator has seen the power of using light directly as a source of electrical power. Essentially what happens in these solar powered devices is a type of semiconductor material in which light falls on causes electrons to be essentially knocked loose, and those electrons then begin to flow out through wires on the side, and then that wire of course produces an electric current. So you directly turn the sunlight into electrical power. one of the advantages of this is that you can do it directly at the user's source. So this could be solar panels on a house where the electricity stays completely in the house and reduces the transmission of that electrical power to this object. A number of states have adopted solar-powered streetlights. This is really a brilliant way of using electrical power directly at the source. Now we can also use a technique called CSP, or concentrated solar power, where we essentially use reflective surfaces to focus the light on a point where we have either water, or oftentimes they use salts, to produce tremendous amounts of heat. You concentrate the power of the sun to create an enormous temperature, which then is used to heat water. The water turns into steam, and you essentially have a turbine engine producing the electrical power. And so again, this is referred to as CSP, concentrated solar power, and these solar powered farms, as they're typically called, take a number of different forms. And so this gives you some of the ideas of what those different forms may look like. They don't all look the same, but they ultimately work on the same principle, and that is that they simply heat water to turn a turbine engine to produce electrical power. Although solar power might seem like a really smart way to take advantage of the sun's energy, unfortunately it's not equal everywhere. So this map shows you where the solar intensity is the greatest, where we get the most energy. And although every place to the right of that red area on the map typically should receive the same amount of solar energy, they produce less kilowatts per hour per day because of the fact that they are oftentimes cloudy. Also, there's the issue of how far north or south you are. The closer to the equator, the more intense the sunlight, and so therefore the more energy you can generate. So it's a combination of your latitude, how close to the equator, and how much cloud cover you have. And so much of the eastern United States receives a lot of cloud cover, and so therefore is not able to produce as much electrical power as the southwest United States, which is very dry and rarely sees clouds at all. Another way we take advantage of the power of the sun is through what's called hydroelectric dams. And the reason why it's taking advantage of the power of the sun is because the sun causes water to evaporate. The evaporated water rises up as a fact that it's being heated, continued to be heated by the sun. As it rises and then moves over the land, it drops the water onto the surface of the land. Now some surfaces of the land are actually quite high. And so what has essentially happened is the energy of the sun has been turned into the potential energy of the water. And so the way that we recapture that energy then is to create something called a dam, where we block the water and we create an elevation difference between the back side of the dam and then the front side of the dam. And as a result of this difference in elevation, the water literally falls down through. That energy, which was in the form of potential, turns into kinetic. That kinetic turns the turbine, and the turbine turns the generator. Now, we have created dams all over the world. One of the most famous in the United States is the Hoover Dam. And typically, when you produce the dam, what ultimately ends up happening is, on the back side of the dam, you produce a lake where you've stored up the water. You've allowed the water to raise its level higher than it would normally be, and that's where we've captured that potential energy. The Hoover Dam was one of the dams that was built during the Great Depression, partially to keep people busy at work, but that dam produces all of the electrical power that's needed by the city of Las Vegas. And of course Las Vegas uses quite a bit of electrical power. It's an extremely high dam, and created also in addition a recreational area called Lake Mead. Now, not all dams are so dramatic. Many dams are much smaller. This is one that's in Japan, and it's a much smaller elevation. It only produces a small amount of electricity for the local surrounding area, but it works on the same principle. Now, in Illinois, we have dams, but of course our dams are not very high because we don't have very high elevation. We don't have canyons in the way that they do in other places, so the elevation is typically much smaller, but still works on the same basic principle. Typically, these are used in very fast-moving rivers, so that it's not just simply the height of the river, the water falling, but it's also a combination of the speed with which the water is already moving. And so now we're going to look at another form of energy which ultimately derives from the sun also. Just like the elevation of the water, the wind is a direct result of the heating of the atmosphere of the earth, and that causes the air to move. Now, as the air moves, of course, we could put the turbine blades directly in front of it. Instead of using steam to turn the turbine blades, we create enormous blades that capture the power of the wind and turn the kinetic energy of the wind into electrical energy. And the way that it occurs is that rather than having one large turbine, we have hundreds of turbines. So you can see that the turbine blades are the big blades of the wind powered device, and then inside the top portion up there is a small electric generator. So the blades turn, that turns the electric generator, and the generator collects the electrical power. And these whole devices can turn so that they face the wind. Now you can see that the way to take advantage of the wind power is through the size of the blade. While a 1-meter blade produces less than half a kilowatt of power, an 11-meter blade, only 11 times longer, produces 47.5 kilowatts. So that's why these blades are so enormous, because they want to collect a large surface area. Now, like with any energy source, not every place is as windy as others. So the places where you see the dark blue, this is where we're having a lot of wind and we can produce a lot of power through wind. Places like the southeastern portion of the United States, unfortunately, the winds do not produce enough speed to really produce significant amounts of wind power. And so we typically see most of our wind power, or our wind farms, are near the mountainous regions like the Rocky Mountains. Another source of energy which is actually related to the wind is called waves, and that's because waves are what cause the waves on the surface of the water. So we've been able to capture the energy of waves by simply taking a device that floats in the water and is connected to the ground underneath, and then as the waves move up and down, it moves a coil of wires around a magnet, and as it does so, it creates an electric current. It doesn't produce a tremendous amount of current, but of course we can create these wave farms where we produce large amounts of current by having a large number of these. Now another way that we can do it is to create what are called capture chambers near the surface of the land. And these are places where air is trapped inside the capture chamber. As the waves move up and down, they force the water inside the capture chamber to go up and down. This creates very high pressure, and the high pressure causes the turbine to turn. Now as the waves go down, a door opens which allows new air to come in, so that when the waves come back up, the air chamber will be filled with air and continue to turn the turbine. It's another sort of ingenious way of producing energy from the wave motion that would normally be totally wasted. So finally, we can examine one of our renewable resources, which is actually not based on the sun, and that is energy directly from the earth. And this works on a fairly simple basis. There are certain parts of the earth where excessive amounts of heat, this is partially the heat that was originally created when the earth formed, and it's still trapped inside the earth and still escaping from the earth. And some of it is as a result of what we believe to be relatively high concentrations of radioactive materials, which also create a lot of heat and keep the earth nice and hot. So essentially what happens is we inject water down into those regions where we know the earth to be very hot, and what comes up through it is very hot water in the form of steam, and that turns a turbine engine, and then we can produce electrical power. It turns out that for Europe, it was actually cheaper at the beginning of the Industrial Revolution to send their metal ore to Iceland, where there is tremendous amounts of geothermal power, in order to take advantage of the electrical power that they could produce and the heat that they could produce through the geothermal source. It was actually cheaper to ship the metal over there, the ore, produce the steel and the iron, and send it back to Europe than it was to make it in Europe. Our last source of energy is called tidal energy, and this actually is essentially the energy that's stored in the gravitational field between the Earth and the moon. The sun does have a little bit of an effect on the tides, but the moon is the main effector, and what essentially happens is that the moon pulls up the water on the Earth to a high point on the places that face the moon and face away from the moon. As the water rises, we build devices which allow a small difference in elevation to force water through turbines, and then when the tides go down, the water reverses its flow and goes in the opposite direction, and we can produce electricity going both ways. Now we've actually produced these devices. England would be a good example. London produces a significant amount of power through tides. It also allows them to have a way of controlling the water, because oftentimes the tides rush up the rivers and then have a tendency to create floods. And so it serves a dual purpose of being able to control the water, the oceans, which would tend to rise and come up the rivers, and then also be able to produce electrical power. And most importantly, you can produce the power whether the tides are coming in or going out. So in closing this topic, the worldwide energy consumption has continued to skyrocket. And if you remember looking at our graph from the beginning of how do we get our energy, this is from 2004. The big issue is that most of our energy is coming from non-renewable sources that will eventually run out. The coal, the oil, the gas, the nuclear fuel, they will run out, and we need to transition to the renewable sources.